Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 2, Projection Section Perspectivity, Elementary Configurations. Section 18, the Quadrangle-quadrilateral configuration. On the left, definition: a complete plane four-point is called a complete quadrangle. It consists of 4 vertices and 6 sides. 2 sides not on the same vertex are called opposite. The intersection of 2 opposite sides is called a diagonal point. If the 3 diagonal points are not collinear, the triangle formed by them is called the diagonal triangle of the quadrangle. On the right, definition: a complete plane four-line is called a complete quadrilateral. It consists of 4 sides and 6 vertices. 2 vertices not on the same side are called opposite. The line joining 2 opposite vertices is called a diagonal line. If the 3 diagonal lines are not concurrent, the triangle formed by them is called the diagonal triangle of the quadrilateral. Assumptions A and E, on which all our reasoning is based, do not suffice to prove that there are more than 3 points on any line. In fact, they are all satisfied by the triple system 1 on page 3, chiefly figure 17. In a case like this, the diagonal points of a complete quadrangle are collinear, and the diagonal lines of a complete quadrilateral concurrent, as may be readily verified. 2 perspective triangles cannot exist in such a plane, and hence the Desargues theorem becomes trivial. Later on, we shall add an assumption which excludes all such cases as this, and in fact provides for the existence of an infinite number of points on a line. A part of what is contained in this assumption is the following. Assumptions H0. The diagonal points of a complete quadrangle are non-collinear. Many of the important theorems of geometry, however, require the existence of no more than a finite number of points. We shall therefore proceed without the use of further assumptions than A and E, understanding that in order to give our theorems meaning, it must be postulated the existence of the points specified in their hypothesis. In most cases, the existence of a sufficient number of points is ensured by assumption H0, and the reader who is taking up the subject for the first time may well take it as having been added to A and E. It is to be used in the solution of problems. We now return to a further study of the Desargues configuration. A complete space 5-point may evidently be regarded in 5 ways as a tetrahedron and a complete 4-line at a point. A plane section of a 4-line is a quadrangle, and the plane section of a tetrahedron is a quadrilateral. It follows that, in 5 ways, the Desargues configuration may be regarded as a quadrangle and a quadrilateral. Moreover, it is clear that the 6 sides of the quadrangle pass through the 6 vertices of the quadrilateral. In the notation described on page 41, one such quadrangle is P12, P13, P14, P15, and the corresponding quadrilateral is L234, L235, L245, L345. The question now naturally arises as to placing the figures thus obtained in special relations. As an application of the theorem of Desargues, we shall show how to construct a quadrilateral which has the same diagonal triangle as a given quadrangle. We will assume in our discussion that the diagonal points of any quadrangle form a triangle. Let P1, P2, P3, and P4 be the vertices of the given complete quadrangle, and let D12, D13, D14 be the vertices of the diagonal triangle, D12 being on the side P1, P2, D13 on the side P1, P3, and D14 on the side P1, P4, figure 18. We observe first that the diagonal triangle is perspective with each of the 4 triangles, formed by a set of 3 of the vertices of the quadrangle, the center of perspectivity being in each case the 4th vertex. This gives rise to 4 axes of perspectivity by theorem 1, one corresponding to each vertex of the quadrangle. These 4 lines clearly form the sides of a complete quadrilateral whose diagonal triangle is D12, D13, and D14. It may be readily verified by selecting 2 perspective triangles that the figure just formed is indeed a Desargues configuration. This special case of the Desargues configuration is called the Quadrangle-quadrilateral configuration. Exercises. 1. If P is the polar of P with regard to the triangle ABC, then P is the pole of P with regard to the same triangle. That is, P is obtained from P by a construction dual to that used in deriving P from P. From this theorem it follows that the relation between the quadrangle and the quadrilateral in this configuration is mutual. That is, if either is given, the other is determined. For a reason which will be evident later, either is called a covariant of the other. 2. Show that the configuration consisting of 2 perspective tetrahedra, their center and plane of perspectivity, and the projectors and traces may be regarded in 6 ways as consisting of a complete 5-point P12, P13, P14, P15, P16, and a complete 5-plane pi 3456, pi 2456, pi 2356, pi 2346, pi 2345. The notation being analogous to that used on page 41 for the Desargues configuration. Show that the edges of the 5-plane are on the faces of the 5-point. 3. If P1, P2, P3, P4, and P5 are vertices of a complete space 5-point, the 10 points Dij, in which an edge Pij meets a face PKPLPM, IJKLM, all distinct, are called diagonal points. A tetrahedra P2, P3, P4, P5, and D12, D13, D14, D15 are perspective with P1 as center. Their plane of perspectivity, pi1, is called the polar of P1 with regard to the 4 vertices. In like manner, the points P2, P3, P4, P5 determine their polar planes pi2, pi3, pi4, pi5. Prove that the 5-point and the polar 5-plane form the configuration of 2 perspective tetrahedra, that the plane section of the 5-point by any of the 5 planes is a quadrangle-quadrilateral configuration, and that the dual of the above construction applied to the 5-plane determines the original 5-point. 4. If P is the pole of pi with regard to the tetrahedra A1, A2, A3, A4, then is pi the polar of P with regard to the same tetrahedron?
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.